Pindyck, his course lecture from 2017, provides a set of critiques on these integrated assessment models. I read from his page 349, putting aside the discount rate problem. Because of the current limitations of climate change science, these models simply make assumptions about climate sensitivity. That is, the temperature increase that would result from a doubling of the atmospheric carbon dioxide concentration. The figure and table taken from Stern 2008 give some idea of the uncertainty in this climate sensitivity. The figure gives 95% confidence intervals of eventual warming for different carbon dioxide equivalent concentrations. And the table shows likelihoods of exceeding a certain temperature increase for different carbon dioxide equivalent concentrations. The quote from Perman continues, the models likewise make assumptions about the damage function, that is, the relationship between an increase in temperature and GDP. In my reading of the literature, the assumptions on the damage functions are most problematic. In an earlier paper from 2013, Pindyck points out sometimes these numbers are justified by referring to IPCC or related summary studies. For example, Nordhaus points out that the 2007 IPCC report states that global mean losses could be 1 to 5% GDP for 4 degrees Celsius of warming. But where did the IPCC get those numbers? From its own survey of several integrated assessment models. Yes, it is a bit circular. The bottom line here is that the damage functions used in most integrated assessment models are completely made up with no theoretical or empirical foundation. I do not want to give the impression that economists know nothing about the impacts of climate change. On the contrary, considerable work has been done on specific aspects of that impact, especially with respect to agriculture. Statistical studies of this sort will surely improve our knowledge of how climate change might affect the economy, or at least some sectors of the economy. But the data used in these studies are limited to relatively short time periods and small fluctuations in temperature and other weather variables. In other words, the damage functions used to estimate the social cost of carbon are either completely arbitrary or need to make considerable out-of-sample predictions. We return to the theme of valuing nature and impacts next week. Returning to the quote by Pindyck 2017, and the models which generally focus on the most likely outcome tell us nothing about tail risk, that is, the likelihood and possible impact of a catastrophic climate outcome and the key driver of the social cost of carbon. Weizmann once described the social cost of carbon as a battle between the discount factor and catastrophic damages contained in tail risks. Finally, Pindyck brings these concerns together in saying, the difficulty with the use of integrated assessment models for policy analysis goes beyond their arbitrary parameter assumptions and ad hoc damage functions. The greater problem is that they create a perception of knowledge and precision that is illusory and can mislead policymakers into thinking that the forecasts generated by the models have some kind of scientific legitimacy. For further illustration, consider the following. Estimates for the marginal external cost are only valuable if we are indeed, as assumed, on the optimal consumption path. In the figure, we see depicted that if the optimal consumption path were different, the social cost of carbon estimates need to be either higher or lower. Pindyck instead proposes to use an average social cost of carbon, rather than the marginal social cost of carbon that are estimated with these integrated assessment models. He does so for the following reasons. First, as we just pointed out, the estimation of the marginal social cost of carbon assumes that we are on an optimal path. Second, unlike the marginal social cost of carbon, the average social cost of carbon remains fixed for a period of time, providing stability for investors. Third, the average social cost of carbon estimates are less sensitive to the discount rates because one discounts the benefits from a larger set of emission reductions or path of reductions rather than from 1 ton of change in current emissions. Fourth, Pindyck proposes to calculate this average social cost of carbon using expert opinions. This does not rule out that various experts may wish to use their best integrated assessment models, yet Pindyck mentions that this method is at least open about the subjective nature of the estimate, and he proposes a relatively tractable way to estimate it. Here we see the results of Pindyck's exercise of estimating the average social cost of carbon for the coming 50 years, using responses from both economists and climate scientists separately. Which estimates would you tend to trust more? And would you prefer estimates from the marginal or average social cost of carbon?